Bismillahirrahmanirrahim. So let us consider mesh analysis in the frequency domain. So for this, let's consider a simple circuit. We have a J10 ohm impedance here, which is an inductor, then a 10 ohm resistor here, and a minus J10 ohm impedance, 10 ohms. This is J10 ohm, and this is 10 volts, right? So we are interested to solve this using mesh analysis. So let's uh, suppose two currents in the two loops that we have. So the directions of the current can be chosen in many ways. So let us consider this direction here, I1, and the same direction for I2 here. Both the directions can be chosen in counterclockwise direction also, in this direction also, or one can be in the clockwise direction and the other can be in the anti-clockwise direction, and even another one can be inside the outer, there can be an outer loop also. So let's uh, call this method one to solve this circuit, right? So uh, the voltage drops here and the voltage sources here, their sign can be chosen using two different conventions. For example, we can either choose this as minus 10 when the current is entering this voltage source from the negative terminal, we take it negative, and when it is entering it from the positive terminal, then we can take it as positive. So this can be minus 10, and then the voltage drop here will be taken as positive across an impedance, it will be taken as positive, that will be J10 I1. So impedance multiplied by the current, this is the potential drop here, the voltage drop here. And the current through this resistor, there are two currents flowing through it. One is I1, it is in this direction, and I2 is in the opposite direction. So the net current is I1 minus I2. So that is 10 into I1 minus I2. And these are all three potential voltage drops here, 1, 2, and 3, and their sum is equal to 0, right? So alternatively, we could take the opposite signs here. We could take this when the current entering from the negative terminal, we can take it this as positive here, but then this will be minus J10, and this will be minus 10 into I1 minus I2. And we will use the same convention for the second loop also. So whatever convention we use in the first loop, we will use the same convention in the second loop. So this is equation for the first loop. Let's simplify it. So the constant will be taken on the right side. So this is J10 I1 and this is 10 I1. So that is 10 plus J10 I1, right? And then we have minus 10 I2 and the constant here 10. So we see we can divide this whole equation by 10. So that will be 1 plus j I1 minus I2, and that is equal to 1. And that's our equation number 1 for loop number 1. So we can write the equation for the second loop also. And now again the net current here in the 10 ohm resistor is I2 and minus I1. I2 minus I1 multiplied by 10, and then minus J10 I2 is equal to 0. So this will be minus 10 I1 and then plus 10 and minus plus 10 and minus J10 I2 is equal to 0. Again, this equation can also be divided by 10. So that will be minus I1 plus 1 minus J I2 is equal to 0. So this is our second equation. So we have two equations now. So let's multiply equation 2 by 1 plus j, right? So this is minus into 1 plus j I1 plus 1 plus j into 1 minus j. So that will be 1 plus 1, right? 1 square plus uh, j square. So that will be 1 here. So that's I2 is equal to 0. So we have minus 1 plus j I1 plus 2 I2 is equal to 0. So what I've used here to illustrate this, just see, if we have a plus jb into a minus jb, this comes out to be a square plus minus jab, right? And then plus jab, and then uh, plus jb into minus jb. That is a square. This cancels out, right? And this is j square. J square is minus, and this minus sign again is also present. So that is plus b square, right? So uh, 1 plus j into 1 minus j here, right? 1, we multiplied this equation by 1 plus j, right? So this is minus into 1 plus j I1, and then 1 plus j into 1 minus j is equal to 1 square plus the coefficient of j is 1. So b is 1 here, a is 1 here, so that will be 1 square plus 1 square, that will be 2, right? So this is 2I2 is equal to 0. So this is the modified form of this equation number 2, and we call it this equation number 3. And let's add this equation 1 here. So 1 plus j I1 minus I2 is equal to 1. If we add this equation, so this will be I2 is equal to 1. I2 is equal to 1 ampere, right? And substituting this value of I2 here, we obtain the value of I1. So I1 is equal to 1 minus j into 1, so that is simply 1 minus j ampere, right? So this is the value of current I1. This is 1 minus j ampere, and this is the value of current I2, which is 1 ampere. So we see that the current flowing through this inductor is 1 minus j ampere. The current flowing through this minus j10 ohm impedance is 1 ampere. And the current flowing through I10 can be found by subtracting I2 from I1, right? So this is one way to solve this circuit. And as we have discussed, there are other ways to solve the circuit also. For example, we can take the loops in the opposite direction, or one loop in one direction and the other loop in the other direction. So for example, we can take both the loops in the counterclockwise direction and then solve this circuit. So I leave it to you, but method 2, we can assume this is 10 volts here, this is j10 ohm, this is 10 ohm, this is minus j10 ohm. So let's assume direction for this current the same as the previous one, and let's assume this direction here. So let's call this current I3 and I4. So the direction of I4 is now opposite to that of I2. The direction of I3 is the same as that of I1. So when we solve this, we should get I3 the same as I1, but the I4 we should get the opposite, that of I2. So let's write down the equation for I3. So this will be the same as equation here. So that is minus 10 plus J10 I3 plus sorry, it will be different, because here I3 and I4, they are in the same direction. I3 is in this, have this direction. I4 also has the same direction. So the current through this resistor, both the currents have the same direction, so they will be added together instead of being subtracted here like this. So because here the direction of I1 was downwards and the direction of I2 was upwards, so the net current was the difference of the two currents. Here both the currents have the same direction, so the net current is the sum of the two currents. So that will be 10 into I3 plus I4, and that should be equal to 0. So that's basically 10 I3 plus 10 J3. So 10 plus J10 I3 plus 10 I4, and the constant, that is 10 here. So we can divide this whole equation by 10. So that is 1 plus J I3 plus I4 is equal to 1. And let's call this equation 1, 2, 3, and let's call this equation 4. Now for the second loop, and here both the currents have the same direction. So this will be 10 into I3 plus I4 and minus J10 I4 is equal to 0. So that will be 10 I3, right, plus 10 minus J10 I4 is equal to 0. Again, we can divide this equation by 10. So that will be I3 plus 1 minus J I4 is equal to 0. And let's call this equation number 5. So we have two equations here. 1 plus J I3 plus I4 is equal to 1. And I3 plus 1 minus J I4. So let's multiply this equation 5 with 1 plus J. So that is 1 plus J I3, right? And then 1 plus J into 1 minus J. So that will be 1 square plus 1 square, that is 2 I4 is equal to 0. So we can subtract this equation, equation number 4, from equation 5, right? So this is the modified form of equation 5. So we get 1 plus J I3 plus I4 is equal to 1. So let's subtract this equation. Uh, so what we get is 2I4 minus I4. So that is I4, and that is minus 1 ampere. So as you can see, I2 here was it was in this direction. It was in the clockwise direction. What I4, which is corresponds to I2 here, is in the opposite direction, right? So the sign for I4 is the different, is opposite to that of I2, but the magnitude is the same, right? So similarly, uh, uh, let's find I3 now, which we can find by substituting the value of I4 here in equation 5. So I3 is equal to minus 1 minus 4 minus 1 minus j I4. So I4 is minus 1, so I3 is equal to 1 minus j ampere. So this is the same value uh, as that of I1 in this method. So be- because the direction of I1 is the same as the direction of I3, so the magnitude and the sign for both the currents is the same. Still, we can solve it by many other methods, but one other method that is interesting to illustrate is the use of an outer loop. So let's suppose, let me redraw this circuit here. So this is J10, this is 10 ohm, right? This is minus J10 ohm, this is 10 ohm, this is J10 ohm, this is 10 volts, And let's assume a current here. Let's call this I5, and let's assume an outer loop here this way. Let's call this I6. Actually, we need to assume loops in such a way that each circuit element has a current, at least one current through it. So the equation for this I5 can be written in a similar manner that we wrote equation for these the previous two methods. So this is minus 10 plus J10, and there are two currents flowing through J10 here. One is I5 and the other one is I6. So, and both have the same direction. So that is I5 plus I6, and then 10 I5. So there is only one current flowing through I5 through 10 ohm resistor, that is I5, and that is equal to 0. So 10 plus J10, 10 plus J10 I5 plus J10 I6 is equal to 10. And dividing this whole equation by 10, this is 1 plus J I5 plus J I6 is equal to 1. So this is our equation number 6. So let's now write the equation for the outer loop, the current I6. So that is again minus 10 plus J10 into I J10 here, I5 plus I6, and minus J10 I6 is equal to 0. So that will be uh, J10 I5 plus J10 I6 minus J10 I6 is equal to the constant term 10. So this J10 I6 cancels with this J10 I6, and we have uh, I5 is equal to 10 over J10, that is minus J ampere. So I5 is minus J ampere. So you will wonder, perhaps this result is different from the previous results, because we had I1 is equal to 1 minus J here, and I2 is equal to 1 here, and there is that is just minus J ampere here. So basically this I1 here represents the current through this J10 ohm impedance, and that current is 1 minus J, and this I2 here represents the current through this minus J10 ohm capacitor, and this is 1 ampere. But note here that the current through this inductor is the sum of two currents, I5 plus I6. The sum of two currents, I5 plus I6, will be should be the same as here, which is just I1. So let's find this second current I6 first. Uh, this is the equation number 7. So we substitute I5, the value of I5 here, which is minus J. So that is minus J here, right? Minus J into 1 plus J I6 is equal to 1, right? And we can divide this whole equation by J. So that will be minus 1 minus 1 plus J plus I6, and that is 1 over J, and that is minus J. So that will be I6 is equal to minus J plus 1 plus J. So that is 1. So I6 is equal to 1 ampere. So note now, the current through this minus J10 ohm capacitor was I2 here, and the I2 was 1 ampere. Again, the current here through minus J10 ohm capacitor is this single current I6 here, and this is again 1 ampere, and the direction of both the currents is the same, right? Here we assumed a different direction, and the answer was with an opposite sign but with the same magnitude. And the current through this inductor here was just I1, single current I1, and the single current I1 was 1 minus J. Here, the current through the inductor is the sum of the two currents I5 plus I6. So the current through the inductor, if you add together I5 plus I6, will again be 1 minus J. So current through the inductor IL is still same. I5 plus I6 is 1 minus J ampere. So the current through this inductor, if we want to find out, still remains the same. And the current I5 here also represents the current through this resistor, and I5 is minus J ampere. If we calculate the current here through this resistor, so that will be I1 minus I2. So that answer should still come out to be minus J ampere, right? I2 and I1 minus I2. So I1 minus I2 gives the same answer as minus J ampere. So this solution, and this solution, all three are consistent with each other.